Day 3. Everybody's got their notes out, ready to roll. We're on the second or third page, I think. Get your pencil out, get ready to write stuff down. As a quick review, a solute is what we dissolve, right? A solvent's what's doing the dissolving. Putting those two together, we get a solution. We have several different solutions. Last time we worked with molarity. Molarity is moles of solute over liters of solution. So it was moles of solute over liters of solution. So we're going to do one, just a refresher problem. So if you want to add this to the side or whatever, you can add this to the side. Here I have a volumetric flask, and in the volumetric flask I have 0.5 liters. I know the concentration in the flask is 0.200 molar. But I want to know how many grams of potassium nitrate did I have to put in there to get that. So we're going to do a little back thinking, okay? So I know molarity is equal to moles over liters, right? Moles of solid over liters of solution. So I have got molarity and I've got liters. So if I rearrange this equation right here, I can say, oh, well, moles are equal to molarity times liters. Everybody okay with that? Now I can just plug in. Let's see what we can plug in and get. So I want to figure out moles. I'm going to go molarity 0.200 molar times liters, 0.5 liters. And if I times those together, what am I going to get? If you don't have your calculator out, you're going to want it out now, or use a phone as a calculator. You're going to need it today. So get it out. 0.1 it should be. 0.2 times 0.5, 0.1. And we really don't need that 0 right there. Let me see if I can erase that. Because we only have one significant figure, and that's the 5 right there. That 0 in front doesn't count. So that would be 0.1 moles of KNO3. Well, that doesn't tell me how many grams that I have. So now I have to use the mole map. I have to go from moles in the center to on our one up front, grams on the right. So I need to find out how much a potassium nitrate weighs. So I look on the periodic table. Potassium is 39.098, and I've just done it so many times I know. It's number 19. Nitrogen is 14.007, and we have 3 oxygens. So we're going to go 3 times 15.999. I am not doing this in my head. I do not remember what it is. I need your help. Please add that up. And you can add this to another area of your notes that I haven't written down, so you have another example. Does anybody have that added up? Yes, what is it? 101.0102. We're just going to take 5, so that's good. Did everybody else get this? Do okay? We second and a thirded it? Good. That's equal to 1 mole. Thank you for being brave. Sometimes it's hard to be the first one to answer. All right, so now what we're going to do is we're going to take this mole and I want to convert it to grams. So I'm going to do my factor label, or it's called dimensional analysis. There's several different words. I got mole. I want to get rid of mole. So mole's going to go on the bottom. And I want to get to grams, so this, what I just added up, is going to go on the top. And I didn't add it up. You guys did, so thank you. At this point, we can take and we can cancel out moles. And we just take and times those two. So even without a calculator, you should be able to say, oh, 0.1 just means I'm going to move it 1 in this direction. So I'm going to end up with 10, since I only have one significant figure, grams of KNO3 that I put in there. My answer. Done. Okay? We're all right? Everybody followed every step? Anybody get confused before we move on? So the next one we're going to be working with has a lot to do, I don't know why scientists do this. They have, in AP we use different R's. There's different R values, so we have to know what each of the R values are. in regular chemistry, they shorten mole by taking an E off, but they didn't shorten molecule. I don't know why. They're giving you two things that are basically starting the same and just changing a little bit at the end. So I came up with a little ditty. It's not real fancy or anything, but it helps me to remember. So it's molarity, molitery, molarity, molitery, molarity, molitery, moles per liter. Okay? You'll understand in a minute. So molarity, molitery, molarity, molitery, molarity, molitery, moles per liter. Then we come to, we need other concentrations. Molarity won't always work because it's dependent on just the solute. And we have some things that we also need to know what the solvent is, not just what the total solution is. So molarity just doesn't do that. So we have another concentration. It's called molality. Okay, don't use this M. Use an italicized M because that M represents meters, right? It didn't italicize. So it should be an italicized lowercase m. We're using M again. They couldn't pick another letter of the alphabet. That drives me crazy. The word, molality, molarity, molality, they sound the same. Okay, so that's how I put the little ditty together. Molarity, molitery, molarity, molitery, molarity, molitery, moles per liter. Well, molality is moles per kilogram. So when I say molality, I overemphasize molality. It sounds fat. So it's kilograms. Okay, so molarity, molitery, molarity, molitery, molarity, molitery, moles per liter. Molality is fat, so it's kilograms. Okay? And again, don't write it that way. Do a cursive or lowercase m that's italicized. All right, so molality is really important when we're working with industry. It's really hard to measure volumes in industry, but it's real easy to weigh things. I can take a dump truck load of stuff, put it on a big scale, go in, dump it, come back out, reweigh the dump truck, and I know how much has got put into the vat. Okay? On the other hand, it's really hard to take a volume, hook it up, and have some kind of flow meter and decide how much flow is coming through to figure out how much liters I put in. It just is harder. So they use molality. It's a lot easier to work with. I can measure how much is going in. We also use percent by mass. Now, a lot of times they won't put it as percent by mass. They'll put it as pph, and we'll talk about reasons why here in just a second. But it is basically like finding your percent on the test. How many grams over how many grams of solution? How many things did I get right over how many I could have got right? Jacob, you getting this down? You'll want to add this in. If there's not a place for it in your notes, you'll want to add this in. Okay, so pph. Now, as you grow up and you get into your own house, once a year, the city's required to give you a disclosure-like thing about what's in your water. Okay, and it comes with pph, ppm, ppb. We're going to talk about those on the next slide. So as soon as you get this one written down, I'm going to flip to the other one. If they said percent, if they said, there's 10% lead in your water, everybody would go, what the heck? There's what in my water? But if they say 10 pph, people don't get as excited. Why? They don't know what it is. It's sort of like that first week that you were in chemistry, if you were with me. I gave you an article. We read an article that says, we need to ban DHMO, dihydrogen monoxide. We need to ban it. It's horrible. It causes several deaths every year. It, causes damage to the earth, blah, blah, blah. It went on and on and on. But then we figured out what dihydrogen monoxide was. Dihydrogen, two hydrogens, monoxide, one oxygen, H2O. What? We can't ban water. But you know what? Online they've come up with page after page of signatures to ban DHMO. It was a social experiment because people don't know what it is. So if the city has to give you a disclosure and they don't want you to know that it's 10% lead in your water, right? Don't fall asleep, stay awake, you can do it. Okay, they'll put pph. Then nobody's at their door knocking saying, hey. Okay, So let's look at what's the difference. Oh, well, we'll just practice first. I forgot that this is not in the right order, but that's okay. So what's the molality of a solution? This should be on your paper, right? Of a solution that has, and it gives us some stuff. So let's review what molality is. Molality is what? Moles of solute. Stay with me, guys. I know it's hard in the morning and it's a Friday. Over kilograms of solvent. Thank you. I just had one of those moments of death. All right, so let's look at what we've got here. We have got this. What's that? Where does that go? Top or bottom on my equation? Top. It's the moles. So 0.562 moles divided by. Then we have this number right here. And that goes where? Bottom. So we've got 1.34 kilograms. All we have to do is divide those. Let's get an answer. You can do that even with your phone calculators, right? We have 3 significant figures, both places, so we're going to need 3. What are my answers? 419. Do I have a second on that? Second and third. Woohoo! Yay! Right, answer. And we're done. Now, in your worksheet, and you had some on your last one, sometimes they won't give you moles, they'll give you grams, and they tell you what of, right? They did tell me, nope, they didn't tell me what of here. So they might tell you it's 56 grams of sodium chloride. And you've got to figure out what sodium chloride is, the chemical formula, and then add it up. Take the grams divided by what you added up. That'll give you moles. Then you can plug it in. They might give you grams for the solvent. What do you need to do then? Divide it by 1,000 to get into kilograms. Good. Okay, so it's not hard. Take it step by step. Okay? So let's go on to the next one, ppm. This is what I should have moved up a slide before, but I haven't. So ppm is parts per million. pph was parts per 100. What's the difference here in the formula? The only difference in the formula is that. So I still divided the mass of the whatever I wanted to figure out, divided by the mass of the solution. But instead of timesing it by 100 to get percent, I times it by 1,000,000 to get parts per million. And if I want to do 1 billion, I times it by 1 billion. If you didn't know what those were, now you do. Okay? So if it's parts per billion, if they say 10 parts per billion of lead in my water, I'm probably okay with that. I don't like any lead in my water, but 10 parts per billion is a lot better than 10 parts per 100, right? Okay? So we need to look at that. So I'm going to flip out of this just for a second. Go to this behind it. So this was in the paper a couple days ago. This little picture, you know, you always get a nice little picture here. And it says, lead contamination of Flint water draws multiple family lawsuits. Why were they drawing lawsuits? Just from the head here. You guys have been hearing this in the news. Tell me what's going on in Flint. Okay, so they have lead problems now in their water, right? And they can't just switch back because the lead pipes now are starting to corrode and get into the water. They also have a huge incidence of Legionnaire's disease because of it. So there's lots of problems here. Now, how about, did any of you see this in the paper during the summer? Let's see. Let me see if I can zoom out a little bit. Colorado mine wastewater hits New Mexico. And they had, they were showing the sediment coming out, and then later, let's see. And then it was coming down into Lake Powell, and they actually had several different things that they were going on, and people are demanding to know what's going on and why does the river smell bad and is it toxic to us? And the Indian nations that bordered that were really up in arms because they use it for drinking water, they use it for livestock, they use it for watering their crops, and they couldn't use any of that because it was contaminated. You ever think about when you get up in the morning and you turn on the water to brush your teeth, what happens if that water was not clean anymore? What would you do? Okay, they had to bring water in, right? Well, now you're rationing water. What's Flint going to do? A whole city. Think of, okay, Salt Lake, we can't use our water. Bottled water's going to go up in price a little bit, sort of like, you know, it's going to be hard to work with. Come to Urinetown and find out about this. Okay, so there's the play. This is the whole problem. So we're sort of dependent on people making sure our water's clean, right? And so when you get out there and you're consumers, I want you to be smart consumers, okay? Having had this chemistry class, I want you to be able to say, you know what? You can't fool me. You said ppH. I know what that means. That's parts per 100, and you've got a lot of crap in my water, and I want it out, kind of thing, okay? So I want you to be good consumers. So we're going to go on here a little bit. This next one is a dilution equation. This dilution equation helps me when I get chemicals, and I want you to use chemicals in lab, but I don't want you to use that concentrated stuff because you can get hurt real easy. So I dilute it down. And even dilute, we can get hurt if we use it wrong. So I need to figure out how to make the more dilute solution. So here we have an equation, M1V1 equals M2V2. Very simple, and I just plug in. So if my initial molarity, like if hydrochloric acid, is 12 molar, I want to find out what volume I need to put in to make up, say, 250 milliliters of 0.1 molar for you guys. So I need to figure out what to mix. I'm going to give you a few seconds to write this down so you can understand it, and then we'll go through a dilution equation problem. When your eyes are looking at me, then I know that you've got it done. I don't want to rush anybody. I want to make sure you all get this down. Okay, we are going to need your calculators out again for the next problem, so make sure they're out and ready to roll, or your phone if you're going to use your phone as your calculator. I see all eyeballs. Here we go. Okay, so where did I put my pen? I keep bringing them over here. All right. So what volume in milliliters? So I'm looking for volume in milliliters. That's important, milliliters. Of, here's something I'm using. I'm going to call that V1. Oh, not V1, M1. That's the molarity one. Of calcium chloride solution. Okay, I really don't need to know that for a dilution equation. Would you use to make, oh, here is a volume. I'm going to call that V2. And here is a molarity, and I'm going to call that M2. So what am I missing? Oh, I'm missing V1, right? So I'm going to set up this equation. M1 V1 equals M2 V2. I'm going to plug in what I have. I have the first molarity, 2.0 molar. I don't have V1. Equals, I do have the molarity 2, which is 0.300 molar. And I do have volume 2, which is 0.5 liters. Okay, I can see right now that my molarities are going to cancel out because they're on opposite sides. So I'm going to be left with liters. That's a good thing because I'm looking for a volume, right? So I'm going to take and I'm going to times these two together right here on this side. What do I get? .15. Good. And we're just going to take it down like that. We're not going to worry about significant figures till the end. Then I'm going to divide both sides by 2, right? 2.02. I brought the M down, I shouldn't have. And we still had liters over here. So V1 is going to be equal to 0. What? 0.075 liters. Wait a minute, they asked me for milliliters. How do I change from liters to milliliters? Okay, good. In 1 liter, there are 1,000 milliliters. So here my liters would go out, and I would be left with what? $75 milliliters. Now, to put it to the right number of significant figures, I would probably report 80 milliliters. Now, if I was doing this in lab, I still would probably try and measure out 75 because it'll be more accurate. Okay? So, and we would measure out of calcium chloride solution. Okay? So not hard, just to plug and chug, right? A couple of things we need to plug and chug. So we're going to actually be working with how concentrated solutions are here now with our Kool-Aid lab. So let's go to our Kool-Aid lab. Grab that out. Yep, you get to drink it. We're not going back into lab. We're going to do it out here. Okay, so here's my Kool-Aid lab. All right, that's better. All right, I'm going to take a picture of this. We're going to go through different parts of it, so stay with me. You should be able to easily finish this before the end of the period and have some time to work on your worksheet. So, purpose is to determine the Kool-Aid concentration molarity of properly made Kool-Aid. Okay. Method, you get 3 solutions of Kool-Aid at different concentrations and taste them to decide which is the correct concentration. You got materials, instant drink mix with sugar like Kool-Aid. We're going to do stir sticks. You got paper Dixie bathroom cups, water. We're not going to worry about the ruler, but the balances are at the back. You're going to calculate how much solid Kool-Aid you'll need to make 0.1 liters. Now we're actually going to take a bathroom cup like this, and we're going to just put a line all the way across it, just barely down from the top. I've got a picture of one right here that I can show you. So we're just going to take and put a line about that far down on the bathroom cup. And we're going to assume that's 0.1 liters for what we do in lab. Now, the reason why we're doing this is we don't want to use the measurement equipment that's back in lab because it's had chemicals in it. And we don't want to find out exactly what it is because then we wouldn't want to drink it, right? So we're going to do it that way. Okay, so I'm going to take and make a line, and I'm going to say that line right there is 0.1 liters. Now, we know the volume now, and we know the molarity at each concentration, because here's the concentration of each thing. What we need to find out is how much we need to put in to get to that concentration. So, first thing we need to do is to assume all of the Kool-Aid is basically sugar. It mostly is. It's got a little bit of flavoring, but we're going to assume it's all sugar. So first thing we need to do is find out the molar mass. So let's do the molar mass. I have 6 carbons. Each carbon is what? What's the mass of carbon? 1, 1. Good. Okay, then I have 12 hydrogens. What's the mass of hydrogen? Good. And then I have 6 oxygens. What's the mass of them? 15.999. You guys sound like you might have that memorized by now. Remember how you guys looked at me at the first of the year and went, how do you know all those? Because you use them a lot. That's why you know them. Okay, so let's add those all up. And what do we get to? 5 significant figures. 5 significant figures. I need several of you doing that so we can double check each other because that's a lot to calculate. We won't want the wrong number. Huh? It doesn't work on the phone? You can't take this times this plus this times this? Oh no, it should work. You need to download yourself a different calculator. Anybody got an answer, Brave? 180.15616. Okay, do I have a second? Okay, I got a 0.6. I got a different answer. Does anybody else have the 1.6? Okay, raise your hand if you've got this. Okay, awesome. Okay, so that's how many grams are equal to 1 mole. Good job checking each other. Thank you for that. Okay, now we need to figure out the mass of Kool-Aid for this amount. I'm going to do 1 with you and show you how to do it. Then you need to do B and C. Okay? So we're going to take this. We up here said that, remember that molarity equals moles divided by liter. So if we're trying to find grams, which one of those do you think I'm going to solve for? Molarity, moles, or liter? What one's going to get me to grams? Moles. So I'm going to rearrange this and solve for moles. So moles are equal to molarity times volume, right? Well, we have, here's our liters, and here's our molarity. So we're going to take and times those two together. So 0.1 molar, and that's what's going to change each time because we're changing the concentration, times 0.1 liters, that is not going to change. And we're going to end up with moles. So 0.1 times 0.1 is what? 0.01, okay? You move the decimal one. Okay, now I've got moles. Oh, wait a minute, up here, I just figured out how many grams are in 1 mole. So I can use that to change. So I'm going to do that. 1 mole on the bottom, and I probably should say, oh, this is sugar. So there's 1 mole of sugar, 1 mole of sugar, and this is 180, because I should always label what I'm putting in my stuff so they know. But I don't want to write C6H12O6 every single time, so that's why I gave it a symbol. Okay, so moles go out, times those together. How much do I need to weigh out? .8. I'm just going to go to the 0.8. Now, there's one scale back there that doesn't weigh to the point. So what should I weigh out if I can't? I can only weigh to the whole number. 2. So it's about 2 grams. Okay, and that's my answer for this. And I should put my little sugar. Okay. You all right? Okay, we're going to go down a little bit to where you see those cylinders. Middle of the page. Right here. I forgot to put a little bit extra stuff right here, so I'm going to explain this. And I do need to go back and fix this lab a little bit. So let's talk about this. I put at the end here, draw the relative concentration of Kool-Aid using circles to represent the Kool-Aid in solution, using 1 circle to represent each 0.1 molar of Kool-Aid. But I forgot to say if each cylinder represents 1 liter. So in the first one, 0.1, there's only 1, right? First one, there's only 1.1 moles in 1 liter, because 0.1 divided by 1 is 0.1, right? So I'll just put 1 dot. I'm going to let you guys figure out the other 2. Okay, now, right here, we already told you how to do the cup with a little line on it. So you're going to fill it up to the same place every time. Weigh the cup, not a big deal. This is where we need to flip it. We're not going to weigh it. We're going to basically get rid of that. We're going to zero out balance on that one. And then we're going to add the mass of solid or sugar Kool-Aid that we need and write it down. So if we don't get exactly 1.8, I don't want you to get into your cup and put it back. That's gross. Okay, especially after we do the first trial and you're using the same cup that you drank out of. So whatever solid amount you put, then you put here. You're going to have to divide this into 1, 2, and 3. So you can write down the mass of each one. Okay, so do that right now. Divide that line right there into 1, 2, and 3. Or B, C, and D is what basically it is. Okay, so whatever you measure out actually for B, C, and D. Now, just like when we were making a molar solution, we put the solid in first, then we put the liquid up to the line. Okay, so we're going to do that. So you're going to have your little cup, and you're going to have your little stir stick here, little coffee stir. Okay, and you're going to put the solid in here first, then you'll go over here and I'll have that pitcher filled with cold water, and you'll fill it up to the line, you'll stir it really good, and you taste it. Everybody in your group can have a cup and a stir stick. Okay, if you don't want to drink it, that's fine, but somebody needs to be the taster. If both of you are tasting, you both need to agree on what the perfect solution is for Kool-Aid. Okay, so I know some people like it a lot sweeter than others, but you both have to decide what the best concentration for Kool-Aid is. If after you do these 3, flip on the other side. On the other side, real quick here. If after you do these 3, now you're going to be rating them. You're going to be rating how they looked, what color were they, how deep the color was, how did they smell, because some things will smell a lot better or worse when they're concentrated. How did it taste? And then rate it as 0 to 10, 10 being closest to Kool-Aid, and way it should be tasting, and 0 being, oh, it's so far away, it's gross. Okay? If you don't find your perfect Kool-Aid within these 3, you can do up to 3 more trials. Say, you know what, I really think it's between these first 2. So I'm going to go between those. You've got to calculate your molarity, figure out what molarity you are doing, and taste it and see if you can find that perfect Kool-Aid. Okay? If you found it in the top 3, you're just going to write a line across here and say, we found it. Done. Okay? Then you're going to answer some questions that have to do with the Kool-Aid. Down here at the very bottom, before you do your error analysis and conclusion, I've set up where you're finding parts per million. So you're going to do parts per million for each of those setups. So A is like B on the other side. And only thing that you have to do, I've shown you how to set it up, is put in the mass of sugar right here, and then times it through. Okay? Remember on your conclusion, write it right now. You need 3 sentences. If you don't write 3 sentences, you're not going to get the full credit there. You need 3 full sentences. So put a little reminder there. You need 3 sentences. And error analysis is, you can do little ticks. It doesn't have to be full sentences. We screwed up measuring the water in. We screwed up, you know, or water measurement was off. Or we didn't stir it all the way and there was stuff down at the bottom. Or not all of it dissolved and it was stuck at the bottom. You know, tell me what went on. Okay? Questions? All right, stuff's at the back. I'll get the water going. The cups are up here, stir rod's up here, and we'll see you.